In this chapter, we're going to be discussing polynomial functions and their models. This is from section 5.1. We've talked quite a bit about the quadratic function using transformations, but we're going to take it a little bit deeper. A polynomial function has the form of x to the n power, x to the n minus 1, all the way down to where x is to the first power, and then finally a constant where there is no x. The highest power that is visible is always going to be written first, no matter what the coefficient is. And then the exponents will decrease in descending order all the way till you get to the constant. The domain of any polynomial function is all real numbers. Since there are no exclusions, since there are no denominators, and there are no square roots. The degree of a polynomial is going to be the largest exponent. In this case, the largest exponent would be n. So the degree of this polynomial would be n. So let's look at the following functions down here and determine whether these functions are polynomials, and if they are, we'll state the degree. Here we have a function, it's named f of x, is equal to 5x to the third minus 3x plus 4. And yes, this is a function. And it is a polynomial because it has this form. I realize there are some terms that might be missing, such as x squared, but that just simply means that the coefficient is a 0. All the constants, or all the coefficients in front, must be real numbers, which they are. 5, -3 are all real numbers. And n, the exponent, has to be non-negative. So this exponent may not be negative. It has to be a positive integer, or 0. So let's look at this one. We have square root of 3 times x squared. Yes, this is a polynomial function. It has a non-negative exponent, and it has a real coefficient. This is not a polynomial function. And the reason is because this x in the denominator actually is x. If we wrote it in the numerator, would be x to the -1. This is a negative exponent, since it would be written as a -1 exponent in the numerator, but we slide it to the bottom to make it positive. So since this is actually an x to the -1, we cannot have negative exponents. For part D, f of x equals square root of x minus 3. Again, no, this is not a polynomial, because the exponent of this x will be to the 1/2 power, because it's under the square root. Remember, square root is the same thing as a 1/2 power. And since this x is to a 1/2 power, remember the powers have to be integers. They have to be like whole numbers. So we cannot have a 1/2 power and cannot be fractions. Finally, this last one, this is a polynomial function. Each x has a power that is an integer. This is x squared, which is an integer. X to the third is an integer. It has a coefficient out in front that is a real number, and there are no fractional exponents. So this is a polynomial function. Now we're going to discuss power functions. Power functions are a special kind of polynomial function. A power function is of the degree n, which is a monomial of this particular form. So it just has one term with this highest exponent of this degree. For example, this is 1/2 x to the first power. This is a power function of the degree 1. Negative 3x to the fourth is a power function of the degree 4. On another note, a similar example, if I have f of x which is equal to 3, this actually is a power function. It's a coefficient times x to a power times x to a power. The power just happens to be 0. However, in order to be a power function, we generally like to set n greater than 0 to eliminate this case. So we like to have n at least of a degree 1 or higher. So power functions of an even degree will have n, which is a number that is 2 or 4 or 6, or basically any even integer. An example of an even degree power function we could graph. We already know what the x squared graph looks like, but let's go ahead and graph it again with using a table. If we square negative 2, we get 4. If we square negative 1, we get 1, and so on. So if I graph this over here, we know it's a parabola. Now, let's look at another even degree. Let's take it to the fourth power. If we take it to the fourth power, let's see what that looks like. Negative 2 to the fourth power is 16. Negative 1 to the fourth power is 1, 0, 1, and 16. So it's going to look very similar. I'll do this one in a different color. So this one I'll do in green. So negative 2, 16, which would be obviously like way up here. Negative 1, 1. 0, 0, 1, 1, and 2, 16, which would be way up at the top again. So this graph is going to be a little bit flatter out at the bottom, and then at the same point, it's going to shoot up to its next point a lot faster. So you see that it has the same 3 points in common. Both these graphs have these 3 points in common, but they do behave differently in between. Once the power starts getting bigger, it becomes more flat around the bottom. It starts to hug the x-axis a little bit tighter. It's not as round. And then it shoots up really fast up to whatever its power is, and in this case would be 16. So it shoots up really fast. So some details about these graphs. F is an even function, so the graph is symmetric with respect to the y-axis. The domain is all real numbers. The range, y is greater than or equal to 0, or you could write it in interval notation from 0 to infinity. And the graph will always contain negative 1, 1, the origin, and 1, 1. So regardless what power you take it to, whether it's 2, 4, 6, 8, 10, 12, 100, whatever, it will always contain these 3 points, and it will be a parabola. Let me briefly show you what x to the 6th would look like. X to the 6th would be even flatter. It would still contain these 3 points, and it would hug the x-axis even more and be a little more squared off, and then it would shoot up even faster. Okay? So the higher that the exponent goes, the more squared off it appears to be, but it will always contain those same 3 points. As the exponent n increases, such as from 2 to 4 to 6, the graph becomes more and more vertical. So when x is less than -1 or greater than 1, but for when x is near the origin, the graph tends to flatten out. So that we already discussed. So now let's look at power functions that are of the odd degree. So let's switch to an odd function. So let's first look at the function x to the third power. -2 to the third power is -8. -1 to the third power is -1, and so on. So if I come over here to graph this, we have -2, -8, -1, -1, 0, 0, 1, 1, and 2, 8. Okay. Now let's look at the graph of f of x equals x to the fifth power. Let's raise it by 2 and still keep it odd. Let's see what this graph now looks like. -2 to the fifth power is going to be -32. So we have -2, -32. So that's going to be like way down here. -1, same point, 0, 0, 1, 1. All of these are the same points. And then 2, 32, which would be way up at the top. So when I connect those points together, like that. So you can see, just like with the even function, it becomes a little more square. It hugs the x-axis or flattens out a little bit more towards the x-axis. But it does, in fact, go and shoot out a lot faster and becomes more and more vertical as it goes outwards from 1 and -1. So if I did another one, which was x to the seventh, it would be even more severe. This graph would be very flat, and then it would sharply take a turn and go directly upward, but still passing through those same 3 points. So you get an idea of what the odd functions will look like. Characteristics of an odd function: f is an odd function, so the graph is always going to be symmetric to the origin. The domain is all real numbers, and the range is all real numbers. The graph will always contain -1, -1, 0, 0, and 1, 1. These 3 points. As the exponent n increases, the graph becomes more and more vertical. Let's look at some with transformations. Here we have a graph which is 3 minus x to the fifth. I would like to rewrite this in descending order because it makes it easier to graph. I'm going to put the largest degree first, which is -x to the fifth, and then put my constant at the end. The first graph I'm going to graph here is f of x, which is x to the fifth power. Well, this is an odd function, so I know it's going to contain these 3 points since it's an odd function. The x to the fifth graph is the green graph here. Will contain these 3 points and shoot up. So I know x to the fifth is going to contain these 3 points, So I'm just going to do a rough graph of that. And then in the next one, I'm going to do any multiplications first. There's a multiplication of a -1 in front of the x to the 5th power. So now I'm going to put that negative out in front, which is an x-axis reflection. So any of these points are going to reflect over the x-axis. So now my graph is going to look like this. Finally, we're going to add the 3 on. This adds a 3 on the outside of the function, which means it's going to do a vertical shift up 3 units. So the origin is now going to move up 3 units. This point will move up 3 units and up 3 units. So this is the final graph of this function. Let's try one more. Here we have a graph of x minus 1 to the 4th power minus 2. The first graph, the original power function, is x to the 4th power. You can see that here. So x to the 4th power is even. So an even function will be a parabola and will always contain these 3 points. Since it's higher than the squared, that just means it'll be a little flatter and it'll be a little more vertical on the outsides. Now we're going to do any multiplications out in front. There are no multiplications, there are no stretches, compressions, or reflections. So we can go right into the shifts. This one is saying that we're going to shift. The 1 is saying we're going to shift it right 1 and down 2. So we're going to take this graph and we're going to shift the graph right 1 and down 2. So take this origin and shift it right 1 and down 2. So these are going to be the same 3 points. And we're going to go up from there. And that's my final graph. For the next part, we're going to talk about how to identify the real zeros of a polynomial function and their multiplicities. First, let's discuss what real zeros are. Let's look at a graph. If I draw a graph of a function right here, and let's say my graph, I'll draw in purple. This is definitely a function. It is a function because it passes the vertical line test everywhere. Okay? And these are my y and my x-axes. And I want to define all the zeros. By definition, zeros are the x-intercepts. So this is a 0, this is a 0, this is a 0, and this is a 0. Anywhere it is above the x-axis, like for example from here to here, the graph is above the x-axis. At this point, it touches the x-axis. So it remains above, it touches the x-axis and still remains above. At this point, it crosses through the x-axis. So at this point right here, it crosses through the x-axis, goes to below the x-axis until here, but it remains below the x-axis all of this region all the way to here. So this would be all below the x-axis. At this point, it also touches the x-axis, and then it goes up to infinity, and at this point it crosses through the x-axis one more time. And all of this information is important as we get to start talking about multiplicity and how to find the zeros of a function. So if a polynomial is factored completely, it's easy to solve this equation using the zero product property. For example, let's say I have a function which is x minus 3 squared times x plus 1. Then we know that the solutions of this, what makes this go to 0, are going to be at x equals 3 and x equals negative 1. Those are the only x's that make this go to 0. So we just found the solutions of this function. The solutions are also called the real zeros. The real zeros of a polynomial are also called the x-intercepts. These three words can be interchangeable in a polynomial function. So the x-intercepts of a graph are also the zeros of the graph, which are also called the solutions of the graph. So let's do an example. Find a polynomial of a degree 3 whose zeros are at negative 4, negative 2, and 3. So we're looking for a function with these three zeros. Well, I know the first zero has to be at negative 4. So that means x plus 4 must be a factor. X plus 2 must be a factor because when I plug in negative 2 for x, I get 0. And finally, x minus 3, because when you plug in 3 for x, you get 0. So if I have zeros at negative 4, negative 2, and 3, that means these three factors will be factors of the polynomial. So generally speaking, if x minus 3 to the m power is a factor, then r is called a zero that has a multiplicity m, which is the exponent. So for the polynomial negative 2 times x minus 2, x plus 1 to the third, x minus 3 to the fourth, list all the zeros. First of all the zeros, this claims x could be 2, negative 1, or 3. There is no x out in front, so this negative 2 is simply just a stretch and a reflection. There is no x in the front, so it does not count towards its zeros. Now, the multiplicity is the power of each of these zeros. The 0, 2 has a multiplicity of 1. The 0, negative 1 has a multiplicity of 3. And the 0 of 3 has a multiplicity of 4. And this information is going to tell us a lot about what is happening at those zeros.